Okay, this next section we're getting into is electricity. We're, to some extent, familiar with electricity. When we talk about charge, think about the atom. An atom in its nucleus has protons and neutrons. Neutrons have no charge, hence the term neutron.
Isn't that because they're proton and electron, kind of?
Sort of. I can't remember exactly how they combine, but they're...
You can split it up.
Yes, you can.
You might get other bits.
Exactly. Exactly. Protons are positively charged. Electrons are outside in your orbitals, and they don't orbit the nucleus like a planet orbits the Earth. Your orbital is a probability region where you might find it. You don't really know exactly where it is in there.
So
but
they're
it is
more like
surrounded.
they're vibrating.
What?
They're more like they're vibrating, right?
I'm not positive. It could be. I'm not sure. When we talk about the charge on a proton or an electron, they have the same magnitude of charge. The magnitude we call the fundamental unit of charge. Your book uses a lowercase e to represent it. A lot of times you'll see electrons written with an e with a minus sign up on the subscript. It's the fundamental unit of charge, but it's negatively charged. The fundamental unit of charge is 1.6 times 10 to the negative 19 coulombs. Capital C is our units. It's called a coulomb. That's the unit measurement system we use for charges. So both electrons and protons have 1.6 times 10 to the negative 19 coulombs of charge. The protons are positive, the electrons are negative. When we're working through equations and problems throughout these next few chapters, we don't use E to represent any charge. E is specifically the amount of charge on a proton or electron. To represent how much charge a certain object has, we use a Q. We may use lowercase q, we may use capital Q. Either way, it just represents how much charge. So if we say an object is positively charged, that means it has more protons than it does electrons. It doesn't mean it doesn't have any electrons. It can have electrons. If it's positively charged, it just means that there's more protons than electrons. If it's negatively charged, it has more electrons than protons. If it's neutral, it has equal amounts of electrons and protons. Now, charge is another quantity that's quantized, meaning it has set values. You cannot split the fundamental unit of charge into pieces. You can't divide it up. Fundamental unit of charge, there is a whole charge of at least 1.6 times 10 to the negative 19. You can have multiples of this, but you can't have fractions of that. Does that make sense? So you have to have a certain number of electrons. You can't have half an electron or half a proton. Now, when we talk about charging an object, making it positively or negatively charged, you have to keep in mind that it's the electrons primarily that you're transferring. Protons are very tightly bound in the nucleus of the atom. It takes an atom smasher. It takes big old lots and lots of energy to get a proton out of its nucleus. So if we talk about things being positively or negatively charged, that means we've either given it more electrons or taken some of its electrons away. It's the electrons that we can easily add or subtract from the atoms. So the electrons technically are the ones that are moving when we look at charging or look at current flowing, for example. Benjamin Franklin was actually the one that came up with the whole concept of positive versus negative charge. At the time, he didn't understand, they didn't know what made up an atom, they didn't know how the atom was made or combined together. And so he arbitrarily chose one of them to be positive and one to be negative, and it turns out he was backwards. He called the electrons, what we now know to be electrons, he called them positive, and what we now know to be protons, negative. Mathematically, it worked out, if we talk about current, the flow of charges, whether we talk about the motion of positive charges or electrons going the other way, mathematically it works out to be the same. So mathematically, no one ever changed the definition, but we now know better conceptually what's going on. Now there's a couple ways to actually charge an object. So induction and conduction are the two ways we can charge an object. Conduction requires actual physical contact. Great example is if you're walking down your hall, your carpeted hall in stocking feet, you're kind of rubbing your feet on the floor, and you shock yourself on the doorknob. Conduction is what's going on between your feet and the carpet. Good example, piece of fur, rubber rod. If I rub them together, the energy that I'm putting into this by rubbing them together actually causes electrons to move from the fur to the rubber rod. Now, it might be a little weird to you. Probably when you've talked about charging before and talk about the movement of charges, you talk about conductors. This is not a conductor. This is an insulator. The difference between a conductor and an insulator is how easily it shares its electrons, its outside electrons, with the neighboring atoms. Insulators don't, they're not good sharers. They don't share their electrons with their neighbors very easily. And by their neighbors, I mean each atom sharing with its neighbor. Okay? But you can charge an insulator. Rubbing it will put electrons onto the portion of the rod that I have rubbed. Okay? You can think of it kind of like sticking a knife in a tub of frosting. You pull it out, frosting is on the part of the knife that went into the tub. The charge will stay on this rod wherever I've placed it. There's no charge, there's no net charge down here because that's where I was holding it and I didn't rub it there. So the net charge is only up in this part. And it is negative. I have put electrons on the rod. The fur doesn't hold on to its electrons as well as this insulating rod does. The rubber holds on to its electrons better, so it's the one that takes the electrons from the fur. Now it won't stay charged indefinitely because the charges can exchange with particles and atoms within the air itself, and it eventually will become neutralized. Conductors, so metals for example, they share their outer electrons really easily. One atom to the next, it doesn't really matter where those electrons reside, and so it's really easy to share the electrons from one to another. So conductors, electrons move around very easily. And so when you charge a conductor, the electrons will move around until they are equally spaced apart from each other. I guess I'm kind of implying and assuming you already know that like charges repel each other and opposite charges attract. If you didn't already know that, like charges repel each other and opposite charges attract. So conduction is actual physical contact, so rubbing materials together to cause the electrons to jump from one another. Example, if you've ever taken a balloon and rubbed it on your hair and stuck it on the ceiling for a neat little trick, when you were rubbing it on your hair, that was conduction as well. Okay. Now, induction. I can show you induction with this. It's kind of hard to see. Feel free to come closer if you need to. These are just two little styrofoam balls, and they're coated with a metallic paint. And so the outside surface is conducting, since it's a metallic paint. If I take my rod and charge it up, and hopefully this works correctly for me, as I bring it in, notice they're attracted. They're coming, trying to touch the rod. I'm trying not to let them. That's induction. we're inducing a separation of charge in the ball. Now granted, if they touch, then it's conduction. And notice now after they've touched, now they're repelling. So initially they were attracting to the rod. Once they've touched the rod, they're now repelling. When they touch the rod, conduction, some of the electrons from the rod jumped onto the balls. Not all of the charge from the rod jumped onto the balls. Only the piece that touched the ball. So now these balls are negatively charged. These little pith balls. Since they're negatively charged, and this is still negatively charged, they're repelling each other. Okay. So kind of cool. So what's happening in induction, we have our rod. It's negatively charged on the area that I rubbed against the fur. By negatively charged, I just mean there's more electrons than protons. Our ball is a conductor. The ball originally was neutral. It had the same number of protons and electrons. As we bring this rod close, well, like charge is repelled. The electrons that were on this side of the ball move over here because they're trying to get away from this guy. They're trying to get away from the rod. That leaves a net positive charge on the other side. The whole ball is still neutral. It still has the same number of protons and electrons. All that has happened is that the charge is rearranged. The electrons move to the other side to get away from this rod. So in effect, we're inducing a positive charge on this side and a negative charge on this side. When it touched, that was conduction, because they touched. We still have those charges that went to the other side. We still have the protons that were left behind. Now some of these electrons jump over because they're attracted to that proton. Which leaves our ball now with a net negative charge. When we pull the rod away, that net negative charge distributes itself uniformly over the sphere. That's something very unique about conductors. With conductors, all of the excess charge will always reside on the surface, and it will spread itself uniformly so that they can get as far apart as possible. Now, it is possible, there is a way to make this ball become positively charged. While we have the rod close but not touching, if we touch this other side, it's called grounding it. If we touch the other side, those electrons, well, if they come onto us, to the Earth, then they can be even further apart. The Earth is like the holy mecca of charges. If I can get to the Earth, we can be as far apart as possible and be happy. So if we touch these, the charges will travel through us to the ground, leaving our ball with a net positive charge. And it's not that the protons move around, it's that the electrons that are still in there, this doesn't take all of the electrons off. It only takes the excess ones over on this side off. So there's still electrons in here. The electrons move themselves around so they're uniformly distributed, but because we don't have as many electrons as we have protons, we get a net positive charge. Okay. So induction, bringing the rod close but not touching it. Conduction, letting them touch so charges could physically jump from one to the other. So one of the fun demonstrations. This is a Van de Graaff generator. Van de Graaff generator. Basically inside what we have, there's a rubber belt that goes, it wraps around the top here and goes down into this base and wraps around the base. When it's on, that belt's moving. in the base. I'm not exactly sure what is happening, but it's charging the rubber rod, the rubber belt, sorry. So it's depositing electrons on the rubber belt. I don't know what process it's actually going through to physically do that, but it's depositing electrons onto the rubber belt. While the electrons on the rubber belt, they're going to stay there until they have a path to leave. Okay, they need something to take them off. When the charges make their way up and get up here, well, we now have these little copper wires. So that gives a path for the electrons to jump onto. So they jump onto these little copper wires. This is all conductively connected, so it's all metallic. This dome sits on top of this peak. And since it's all conductively connected, all of the charges, those electrons, swarm to the outside of this ball. They're trying to get as far away as possible. Now, you may have seen this in the past, may not. Anyone want to volunteer? I always have to do it. Do you want to do it?
Yeah, I don't know what I'm doing.
All you have to do is stand on this stool and put your hand on it.
Awesome.
That's it. Now, how long's your hair?
Short.
We'll get a little bit. I might do it too.
Should not really happen.
Number one, he has to stand on the stool because we need to insulate him from the ground. Standing on the ground, even if your soles are rubber, they're not thick enough to disconnect the path to ground. Okay? So go ahead and put your hand on it.
Don't worry, it won't shock you if you have it on when she starts.
I like these.
So these electrons are going to be transported out to the outside of the sphere. Actually, if you look at my arm hairs, he's inducing a charge in me. I think it's affecting me more than you. And so what's happening, by him touching it, he's now extending the sphere. So there's even further for the charges to go out. Yes, you are. And those are charges that are actually jumping off into the atmosphere, the air of the room.
Whoa.
I don't know where I just grounded you.
I don't know. I just grounded the all this.
But yeah, so the electrons, they're trying to get as far away as possible. They go out on the extensions of all your body. Well, your hairs are very, very light, so they go out to the end of your hairs and they're repelling each other, so all the hairs stand on end.
I grounded.
That's okay.
Oh, there we go.
Okay, I'll do it too. Would someone mind, not that I really want to be on video, but my hair will stand up. And I don't think my head's going to be in the shot.
So stop it.
No, just keep it going. I can edit it out. I always come prepared because a lot of people don't like to do it. So I get a great hairstyle. You hear that little...
This is much better.
I just show it a little better with the longer hair. I'm ionizing the air over here. The electrons are actually jumping off my fingers into the air. That's what the sound you hear is. So longer hair makes it more fun. Ruins the hair day for the rest of the day, but that's okay. Okay. Take my hands off. Because I haven't provided a path to ground, I'm still charged. Now, the sparking that you're hearing is from the Van de Graaff jumping to me. Turns out, we're going to talk about what's called the electric field. The electric field is a way to describe how these charges can influence the space around them. If it gets big enough, it actually forces charges to jump. The force on them gets so big that they will just jump to whatever they can. They're jumping to me. Okay. I get down. It should have fallen.
Yeah, it is.
Quite.
A little bit.
So I have now discharged myself. Apparently it doesn't hurt, it just startles me. Thank you. Another fun way to look at it here. This little screw down here at the bottom is connected to the ground wire in the power cord. So I'm going to ground this sphere. And again, like I said, what's building up is an electric field. If it gets big enough, the force on the charges becomes large enough to physically make them jump. The color you're seeing is the ionization of the gas in the room. It's kind of a purplish color. So the charges are physically jumping from the Van de Graaff generator to this little ball. And notice how the ball shakes. The ball shakes when it hits because it's a collision. It's transferring its momentum to the ball. So the ball ends up shaking. So this is all lightning is. There's a charge difference between the cloud layer and the ground. When the field gets big enough, the charges will physically jump from one to the other. And as they travel through the atmosphere, it ionizes the gas. Ionizing meaning it causes the electrons to jump out of the gas. Works a little better. Hey, now it's jumping on me. You can actually smell it if you're up here close. It gets kind of a funky little smell.
Ozone.
Yep. So,
If you ever smell that and you're outside, run.
I would imagine that's probably not a good sign. So, fun demonstration. So conductors. Conductors are good because any excess charge that resides on it will always go to the outside surface of the conductor. That's true for any conductor. That's why you're safe in your car in a lightning storm. It's not because you have rubber tires. Your rubber tires are pointless. The charges reside on the outside surface. They were not going to come inside, so they reside on the outside surface. When there's enough charge built up, it'll actually jump to the ground from your car. Okay. If you've ever seen a Faraday cage, that's what they're doing is they have a big metal cage for you to sit inside so you don't get shocked. They've shown them in some of the movies lately. Okay. Any questions so far?
The reason why it doesn't jump from the car to the ground is because of the tires, right?
No, it will jump from the car to the ground.
But the reason why it doesn't just go immediately.
Just immediately, right, is because of the tires. Yeah, because there's a gap. And so anytime there's a gap, there has to be a big enough field built up before it can jump.
So is it a requirement to make cars out of something that will conduct
I
charge?
don't know.
Yeah, if you've got a Pontiac Fiero, you're good.
Yeah, I don't know. I seriously doubt that is a requirement in the manufacturing. It's convenient, but I don't think car manufacturers decide, what if my passenger happens to be hit by lightning? I don't know. Okay, so charging objects, there's two ways to do it. This was by conduction. Induction, when you don't touch them. The symbols we're going to use to represent charge on an object is Q. Both lowercase and capital Q will work.